Hello and welcome to lesson 1 of complex analysis, and in this series I would be covering directly the mathematic parts of complex analysis. Viewers or subscribers, those who have watched my earlier videos in complex analysis must have seen that I have covered mostly the history, the motivation and little bit about how to study complex analysis, but from today onwards all these lessons will be concentrated only on the mathematics of complex analysis. This is lesson number 1, and in future I would be dealing with the complex analysis, only the mathematics part. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to lesson 1 of complex analysis. Before we start ahead, I would like to tell you something important, that I am assuming that you don't know anything about complex analysis, anything about complex numbers, and thereby I'm building the foundation step by step, one by one, and then I will go into the deep mathematics of complex analysis. So I would like to start with lesson 1, dealing with the mathematics part. Let us see what are the topics that we are covering today. So first we are covering what is called complex number and properties. Then we will cover how to write or represent a complex number. What are the arithmetic operations on complex numbers, examples, what is zero and unity, complex conjugate, what do we mean by that, explaining conjugates with examples. A quick note, those who have seen my earlier videos in quantum mechanics, maybe some part of it is covered, but that is primarily covered keeping in mind that how quantum mechanics and complex numbers are related to each other, but here I am dealing purely with the mathematics of complex analysis. So first I would like to look into what is the complex number and its properties. In general, a complex number we denote as it is any number in the form of z equals to a plus ib, where a and b are real numbers. Now you might have found that a plus ib and a plus bi, both of them are used interchangeably in certain areas of mathematics and certain books, but it doesn't matter, it actually means the same. So if you take a kind of a number like this, z equals to a plus ib, then we means this one to be the real part of z and this is the imaginary part of z. So this is abbreviated as REZ and IMZ. Most of the books use this type of an abbreviation just to make you understand that if you read through this and go through this, understand this is real imaginary part. So if I take an example, z equals to 4 minus 9i, then I means 4 is basically the real part and 9 is basically the imaginary part. So what is meant by a pure imaginary number, although might not sound very relevant to you, but yes, it is important. For a pure imaginary number is basically a real constant which has got an imaginary part. So if I take z equal to 6i, complex number z is said to be purely imaginary because you can see it has got no real part. And two complex numbers are equal if their corresponding real and imaginary parts are equal. This leads us to a very important property which is called equality. Now what do I mean by equality? Let me basically give you a basic understanding. So if I take kind of this constant, say for example z equals to a1 plus b1 and z2 equals to a2 plus b2 are equal if z1 equals to z2 and if a1 and a2 are equals to b2. That means what? That means that I can say that real of z1 is equal to real of z2 and imaginary part of z1 will be equal to imaginary part of z2. I mean to say we can talk about this. So this is actually what is called the equality. Okay, we next come to what is a kind of a syntax or a notation. So the totality of complex numbers or the set of complex numbers usually denoted by this symbol C, because any real number a actually can be written as z equals to a plus 0i, and we generally said that the real number set, that is z r, is basically a subset of C. Okay, now we come to the next important part, that is what are the arithmetic operations. I believe that most of you know, but I will just like to give you a basic understanding of arithmetic operation. So if z1 equals to a1 plus ib1 and z2 equals to a2 ib2, so addition comes under this rule. I think you can just look into it, nothing much, you can find it in internet or other basic lessons. Subtraction is followed by this, multiplication is followed by this, and it leads to this. So this is basically basically a kind of an idea just to give that how do we do the arithmetic operations, because until and unless we understand these things we won't be able to do the further mathematics. Division also follows in the same way, so I will try to solve this one and I will get this one, a1 a2 b1 b2. From here also we can find that the laws of commutativity, associativity are also follows. Here it is the commutative law, this is the associative law, then we get the distributive law and so on. Okay, so now we come to this important property. Now in order to add or for example subtract two complex numbers, we can simply add or subtract the corresponding real and imaginary parts. So that is how we do. And to multiply two complex number, we use the distributive law which we have just in, because the fact is that I square equals to -1. Now you might be thinking that what about division? Now division I will be separately dealing later, because division will require some amount of elaboration. Okay, let me show you some pretty quick examples. How do we do that? So if I take the values of z1 equals to 2 plus 4i, and this one I should be not the subscript, sorry for that, and z1 plus z2. So by adding real and imaginary parts, the sum of two complex numbers, we get this, and finally this is right, yeah. So this will be 1 minus 1 plus 12i. So by the distributive law, I square equal to -1. So the product of z1 and z2 will follow like this and this and this. So if you want, you can take a pause, right, and you can understand that what actually we are doing. So this is simple. We will just add real and imaginary parts separately and we solve this. Don't worry, we will be doing a lot of mathematics onto the operations part. So this would be pretty simple and trivial in the next part. So we get the result as -38 plus 4i. Okay, now we come to a very important property which is called zero and unity. Now the zero in the complex number system is actually the number z plus 0 plus 0i, and the unity is this one, 1 plus 0i. So this part is the 0 and this part is the unity. So 0 and unity are denoted by 0 and 1 respectively. So 0 is actually is this one. If I write it, it looks like this. So 0 and this is basically the additive identity in the complex number system. So for any complex number z equals to a plus ib, we have z plus 0 z plus 0 equals to 0. Now to see this, we can use the definition of addition. Yeah, so we are using the definition of addition, and similarly we get this one, right? So we get how much? A plus ib equals to z, right? So similarly using this similarity, we can use the multiplicative identity by the system, since for any complex number z, we have this one, z into I equals to multiplied by this gives to z, right? So there is also no need to memorize the definition above division, but before that discussing, we would like to introduce another important concept which is called the complex conjugate. Now this is also very trivial. When we talk of complex conjugate, we say that z equals to the number obtained by changing the sign of its imaginary part is called the complex conjugate, and this is denoted by z with a bar on the top. Now some of the books might have a different kind of a notation. It might have a dagger sign, etc., but whatever it is, this is basically the complex conjugate. So z equals to a plus ib can be denoted by this, z equals to 6 plus 3i can be denoted by this. So you can see this, I am just changing the numbers, that's it. So if z is basically a kind of a 8, then z, the complex number, would be this, the conjugate. This is important. The conjugate of a sum and difference of two complex number is the sum and difference of the conjugates, right? So from here we get into this kind of a rule, right? So the conjugate of a sum and difference of two complex numbers is sum of difference of two conjugates. So here I have seen, you see, I have made the sum and then I have made the difference. So from here what we can deduce that there are three more important properties. One is this, that is the subtraction. One is this, that is division, and one is this one. So from here what we can deduce is that the conjugate of any finite sum, we can say, or a product. So for example, finite sum or product of any complex number is the sum or product of the two conjugates. Let me give you an example. So the sum and product of a complex number z with its conjugate z will be this one. right? So that this is something important. These things will come into complex analysis, but before we go ahead with the complexities of complex analysis, these things will be something very important. So sum and product will be denoted by this, and it will be denoted by this. So the first one on the which is red marked box, this is basically the sum, and the next one is the product. So in the same way, okay, let us look back. So this was the sum and product. Now what I'm doing is that I'm doing a difference of a complex number, which is z, is a pure imaginary number. So you see z minus this equals to 2ib. Obviously we have seen that this is a pure imaginary number, just now we have learned. Now since a equals to real of z and b equals to imaginary of z, then this addition will result into this one, and this will result into this one. These are two very important results which automatically comes. I think I don't need to elaborate it further. So this is quite I would say quite clear. So you basically get this one. So this property, if I go back, let me go back, yeah. So this actually has got three important properties, right? The conjugate of any finite sum or product of a complex number is a sum or product of the conjugates, and I have shown you how it happens. And now if I go into this one, right, this one is also equally important. That is, the difference of a complex number is purely imaginary, and from this I would say because a equals to for this it yields to two important formulas, that is real of z equals to and b equals to z. So from here what we can get is this one equals to real of z, z plus z bar, conjugate of 2, and from the this one we get this. So actually what happens is that this actually creates a kind of an important relationship in the discussion, right? So this actually happens from this the addition and this subtraction rule. So we will take a pause of today's video right now, because we have just started with the lesson number 1. Thank you very much for those who are watching this video, and please do support me by subscribing to my channel and clicking on the bell icon of Physics for Students. I'm also available in this email ID very soon. You will get some kind of a good news which I'm quite planning now, and you can also subscribe to my this other channel. You can follow me on my Instagram, Facebook and LinkedIn pages. Thank you very much for watching this video. Remember that I am continuing until the end of complex analysis, and another part would be real analysis until then, but because this is the basic lesson, so it will take some time to build up the basics, and then we will go into the complex calculations of complex analysis. Thank you very much for watching.